Be quiet. All right, so say hi to Fury 2. Hi, Fury 2. You can see what I'm dealing with. Fury 2. Anyway, all right, so we did the demo on why the speed of light slows down when it goes through a denser material. It turns out that we can define a certain property of material called the index of refraction based upon how it changes its speed when light goes through it. And we have this definition of n, index of refraction, being equal to the speed of light, which gets its own variable c, divided by the speed in that new medium. Okay, so what is c again? Speed of light in a vacuum. V is the speed of light in that new medium. And n, the index of refraction, is those two quantities, one divided by the other. So n is a dimensionless number. What does that mean?
Has to be greater than 1.
All right, so it does have to be greater than 1 or equal to 1. But for the top one, dimensionless number, what does this mean? If I take meters per second and divide it by meters per second, what happens to the units? There are no units. They go away. Dimensionless number means that there's no units attached to it. So you know how I often say something like, you have 15 what? 15 butterflies per student? I mean, what 15 cicadas per tree? Yeah, no, it's, in this case, it's just a number. It's just a number. It's a ratio of the two velocities. For a vacuum, n is 1, because what's the speed of light in a vacuum? It's c. So it would be c divided by c. So it's just 1. For air, it's so close to 1, we call it 1. For all of your calculations, for the speed of light in air, we'll just say n is 1. For water, it's 1.33. For any other media, it's always going to be greater than 1. Moving on. All right, so if n is equal to 2, what does that mean? If n equals 2 and c divided by v, what does that mean, yeah? V is half the speed of light. If n is equal to 2, v would be half the speed of light. So whatever material the light is going through, its speed got cut in half because it was getting absorbed and then re-emitted, and that's really probably a very dense material. If n was 0.5, what would that mean? That whatever material is going through, v would be twice the speed of light, but that would disobey the laws of physics, so it's not possible. You can't have that. You can never have an index of refraction of less than 1, because that would mean something that light is going faster than the speed of light in the vacuum, and that's impossible. It's impossible, as far as we know. Maybe one of you someday will figure out how to get light to go faster than 3 times 10 to the 8 meters per second. In which case, I guarantee you would win a Nobel Prize in physics and collect a $1.3 million prize. Yeah, that's it. Just 1.3.
Yeah, it's like that. I want as much money to be like
N can never be less than 1. All right, here are some various indices of refraction. I want you to pick 1 or 2 of those to write on your graphic organizer. I think Crown Glass is on there. Sodium chloride. Did you know that we have government agencies that will use the index of refraction to test out whether or not we are allowed to call something corn syrup? They put light through corn syrup, or what a manufacturer will call corn syrup. But if it does not have the appropriate index of refraction, then that means there's not the correct ratio of sugar to water, and so you wouldn't be allowed to call corn syrup. your corn syrup has to have a minimum index of refraction. Otherwise, you have to call it
Sugar water.
sugar water, or yeah, you're just not allowed to call it corn syrup. They probably have the same thing for honey. Actually, I don't know if that's true or not. But I don't know if honey is protected, but corn syrup is. Why? Because we are a big corn country, so we take our corn syrup seriously. All right, so there's a diamond. This is the my wife let me use her engagement ring for this today. Yes, I am that rich, and she has to wear it on the wrist because on her finger it's just too big. You know, it'd break her finger. So, all right. Let's take a look at a simulation. Here I have a light source, and it's going from air into water. Notice it bends. Here's the question for you. Where's the pause? All right, I'm getting a little ahead of myself, and you need to attempt the. All right, we're back online here. Now, music. Now, at the bottom of the front of your graphic organizer, it asks you to calculate various speeds. Like, what is the speed of light in agua, water? So, Mr. Parker, I have no idea how to do that. Oh, if only there was a method that I taught you to. Oh, wait, VFW. VFW. Okay, what do we do?
Variables.
List out our variables. What are the variables that we know? We know C is equal to 3 times 10 to the 8 meters per second. We know N for water, 1.33. We know that V is equal to, that's what we're trying to find, the speed of light in water. Now, what formula do we use? N equals C over V. Now you got to solve that for V. If I multiply both sides by V, divide both sides by N, the V's cancel out, the N's cancel out, so we have V is equal to C over N. When we put in our numbers, V is equal to 3 times 10 to the 8 divided by 1.33. So V is equal to, what did you guys get? What is it? 2.256. We'll call it 2.26 times 10 to the 8 meters per second. By the way, V will always have to be smaller than 3 times 10 to the 8 because you can never have anything bigger than 3 times 10 to the 8 for speed. All right, so that's for the first one. Pause this. Try to do the speed of light in a diamond. And the next one, using VFW, all right? So substitute, please give them 5 minutes to work through those last two. All right, so make sure everybody's gotten a chance to work through these. The next one was diamond. How do you figure that out? You should have C is equal to, or V equals C over N, 3 times 10 to the 8 divided by 2.49, and that gives you that speed. Again, less than 3 times 10 to the 8. The last one switches around a little bit. It's an unknown substance, but we know that we're given the speed through it. And we know the speed of light, and we're looking for N. So N is equal to C over V. We have an index of refraction of 1.2. Totally made up substance. I don't know of anything that has an index of refraction of 1.2, but it works. All right, so that's that. Yeah, maybe jellyfish. All right, so various indices of refraction. Now we go to a simulation. Turn the page. Here's the big question. What's the big question? What's the big question? The index of refraction for both materials is the same. What will the light do? It'll just go in a straight line. It will not bend. It will just go in a straight line. Alright, so for the next one, that box below, we have air going into water. What does the light do? Going from air into water, it bends. Does it bend towards the normal or away from the normal? It bends towards the normal. What I want you to do is draw out the incident ray, the refracted ray, and the normal. And label them. Basically, yes. Onto your sheet. Okay. Okay. Alright, we're not doing exact measurements. This is all conceptual. So you don't have to actually measure out any of these angles. So normally, if there was no bending of the light would just go in a straight line. But here it does not go in a straight line. It bends towards the normal. So we can say that if the light slows down, because when it goes from air to water, it slows down because water is denser, and so light slows down. When it goes into the water, it slows down, so it bends towards the normal. And this is true always. If the light slows down, it's going to bend towards the normal. I'm going to run out of time. 12 minutes already. Alright, so for the next one. Oh, and label your incident and refracted angles. Theta I and theta R. Remember, everything is always relative to the normal. Always relative to the normal. Alright, so we got one below that. Mr. Parker, why do you have Superman on there? You'll see. So, if we're going from water into air, rather than going in a straight line, it's going to bend, and this time it's going to bend away from the normal. So if the light speeds up, when it goes from water into air, the light speeds up. And whenever the light speeds up, it bends away. So why do I have Superman? Because Superman would say, up, up, and away! And so that's a way for you to remember. If you speed up, it bends away. If it slows down, it bends towards. Alright, so I'm going to stop the video. There will be a second video created that will show you Snell's law. But this is all the conceptual understanding that is essential for refraction. Alright, so period 3, say goodbye. Alright, signing out.